All right, so hello everyone. So we'll keep going with another example that is seemingly very similar to the previous one, except that we have something quite interesting here, is that the small number here multiplies the highest power in x. You see it acts as a perturbation of the highest power, and this is quite an important difference between this case, this example, and the one we had previously. All right, so how do we solve such a problem? We recognize this is a perturbed problem, so we can try it by looking at the n-perturbed. That's the first reaction you should, of course, definitely have. The equation is x minus 1 is equal to 0, which means that x is equal to 1. That's curious, right? Because we would expect 2 roots, but there's only 1 root. And so as we add this small perturbation, there is a second root coming in the problem. And where does the second root come from? You can just take maybe a few seconds or a minute to think about it. You have an idea? So if we start by looking at the problem without the perturbation, so we end up with just x minus 1 is equal to 0, there's 1 root, which is definitely perturbed because of the additive perturbation. But as soon as we add this perturbation, there's another root popping in the problem, and it should come from somewhere. If this is not obvious right now, maybe we'll just have a glimpse at it in a few minutes. Let's try first the expansion method. Expansion method with the regular ansatz. Okay, so we're going to write a regular ansatz, which is x is equal to x0 plus x1 plus epsilon square x2 and so on. Maybe we can do it a little bit faster in this case because we know how it works. So that's the ansatz. Number 2, we substitute the ansatz in the governing equation. So that's epsilon multiplied by x squared to epsilon x0 x1. Then I won't keep the next terms here because that's not the point. x0 plus epsilon x1. I need to keep here epsilon squared x2, right? Because here I stopped at epsilon multiplied by epsilon. So that's epsilon squared. So I need to keep epsilon squared here to make it consistent. And then we have minus 1, and this is something of order epsilon to the third. So at leading order, we have x0 minus 1 is equal to 0. Should make sense to you now that this corresponds to the unperturbed. So it gives x0 is equal to 1. At the following order, we have x0 squared coming from the first term plus x1 is equal to 0. So it means x1 is equal to minus 1. And at the next order, epsilon squared times twice x0 x1 plus x2 is equal to 0, which means that x2 is equal to minus 2 multiplied by x0 x1, so that's plus 2. And the solution of the problem is x0 is 1 minus epsilon plus 2 epsilon squared plus terms of order epsilon to the third, which is in fact I don't show it here. In fact, this is the actual Taylor series expansion of the exact. Okay, that I've not written here, but is something that we could write. All right, and how do we get the exact solution? Okay, so again, I would mean we cheat, although this is not cheating, of course, but we can just have a look at what the exact solution is, because in this case, it is available. In practice, of course, if the exact solution is available, you would not use a perturbation method, except if the exact solution is just cumbersome or way too long, and you would like to determine an approximate solution. So this is 1 over 2a. So 1 over 2 epsilon multiplied by minus b minus 1 plus or minus square root of 1 plus 4 epsilon. And that means if you expand the square root, it means that x behave like 1 over epsilon. This symbol here means behave as, meaning that if I just drop higher order terms, this is the expansion I would get. So minus 1 plus or minus 1 plus, so what comes inside the square root over here divided by 2. All right, that's an expansion we've used already in the previous videos. Minus 2 epsilon square, etc., plus things of order epsilon to the third inside over there, which I dropped. All right, but I don't have to write this because I use the symbol here, behaves as. Okay. And so this means that we have two roots. The first root is x1. In the first root, I'm going to use the plus. Minus 1 plus 1 plus 2 epsilon minus 2 epsilon square, and so on. They cancel. So this is 1 minus epsilon plus things of order epsilon square. Great. Let's see. This is indeed what we got. All right. And second root. This is 1 over 2 epsilon. I need to keep the minus sign, so minus 1 minus 2 epsilon plus twice epsilon square. So this is minus 1, so that's minus 2 over 2 minus 1 over epsilon minus 1 plus epsilon plus things of order epsilon square. All right, and woo! It answers our question. So where does the other root come from? So we have one root in the neighborhood of 1, and the other root, actually, the second root comes from minus infinity. The second root is just traveling from minus infinity as epsilon grows from 0 to small values. All right? And so, of course, the ansatz was not right to capture a root near minus infinity. Let me write it like this. I mean, any mathematician teaching calculus would be frustrated to tell me that a root could be near minus infinity. But we understand as long as we understand each other, we are fine. So, and why isn't it the case? Because when we wrote the regular ansatz over here, remember what we said in the very, very introductory lecture, is that for this to be valid, we need to assume that x0 is different from 0, and that all xi's are things that are of order 1. And so, of course, if x0 is of order 1, there is no way we can capture a root that is going to minus infinity. All right? We can figure this out in a different way, which probably would become then obvious also to you. Let me just represent the problem in its unperturbed case and the perturbed case. So the problem in the unperturbed case is x minus 1 is equal to 0. And so x minus 1 is equal to 0. If you want to sketch it, that's something that looks like this. x minus 1. It is equal to 0 over here, and then I'm supposed to add epsilon times x squared. So epsilon times x squared, this is a very, very flat parabola like this, okay, passing through 0 at this point, meaning that, oops, we have something that looks like this. And so that's the first root that's the first root we have. So it doesn't change over here because this is here that, let me just increase a little bit. Let me just increase a little bit the deformed, the amplified perturbation. All right, it should be tangent over there and then get away again. All right, so what we have observed as earlier is a transition from this root to a root that is located a little bit more to the left. If I would represent this with larger values of epsilon, we would end up with something that looks a little bit more like this. And you understand that the second root is coming from here, second root. And as epsilon grows, actually the second root comes from minus infinity to something that is in the domain, but that is quite large. All right. This brings us to the observation that the problem we are facing here is a problem which is not a regular problem. The problem is singular. All right, that is very important to notice. Why do we notice it is singular? Because the unperturbed problem has not the same format as the perturbed one. By format, I mean we end up with an algebraic equation, but with a different degree. Degree 2 in this case, versus degree 2 versus degree 1. All right? We'll talk again later about singular problems in differential equations. And in differential equations, the problem can become singular if the highest derivative that you observe in the differential equation is higher because of the perturbation than what you have without the perturbation. Okay, this is exactly the same story. Okay, because the problem is singular, then it means it is not regular. All right, so singular is something that is by default opposed to regular. All right, and so part of the problem, although it is a singular problem, parts of the problem can still be tackled with a regular approach, like the expansion method that we used before and the regular ansatz that we used before are things that were fine to get the expansion of the root which is near 1, because the expansion of the root which is near 1 is something that we could get easily with a regular ansatz. All right? Now, we saw that a regular ansatz is something that is not suitable, of course, to capture the second root, which is a root which comes additionally in the problem because it is singular. All right? So we need a different approach for that root. And of course, if we knew in advance, again, that's a little bit cheating, I would say, because in principle, we don't know that. We know it here because we could get the exact solution to the problem. We know that the second root is of order 1 over epsilon. And so let's just imagine for a moment we know this, and let's try to see if we can get this solution by using another ansatz, which could be something like this. All right? So somehow, if you want, the ansatz kind of shapes the form of the solution. And if earlier we said with a regular ansatz, if earlier we said that the solution needs to take that form, then the solution takes that form. And there's no way we can capture that solution. If we now say that in the ansatz that the solution needs to have that form, we should be able to capture that form. All right? Let's just see if we can do it. So what we do, first we use an ansatz, then we push the ansatz into the governing equation. So we need epsilon multiplied by x squared. X squared is this squared plus twice 1 over epsilon x minus 1 x 0 plus x x minus 1 plus x 0 plus epsilon x1 and so on minus 1, and this is equal to 0 plus order epsilon square. I did even too much, I think, here. Let me just correct like this, which is much better, because I truncated the first term here. I truncated to epsilon multiplied by 1 over epsilon, so I truncated to order 1. And so I should keep here things related to order 1, which means that what I dropped is of order epsilon. All right, so let's just expand and collect. We have things coming at the leading order. This is a little strange because the leading now is order 1 over epsilon. We see a few researchers communicating with leading order not being order 1. I would kind of disagree with this, although sometimes, from time to time, I just do it myself too. But this is not purely great. I'll discuss this in a minute. And what do we have? We have x minus 1 squared plus x minus 1 is equal to 0, which means x minus 1 is equal to 0, or x minus 1 is equal to minus 1. This one here is prohibited, right? Because this is the first term. This is the first term in the sequence, and I should say this one is not equal to 0. And all others including this one, should be of order 1, which is the case. This is of order 1, so I'm fine, I can keep it. All right, and then let's keep going. The second term would be of order 1. Next term of order 1 would just tell us 2x minus 1 x0 plus x0 minus 1 is equal to 0. Because this is equal to minus 2. We have 1x0 minus 2x0. We observe that x0 is equal to minus 1. Okay, and then this means that x is equal to minus 1 over epsilon minus epsilon, minus 1 plus things that are of order epsilon. That's what we have right now. And we are really happy because it corresponds to what we had determined by the expansion of the exact solution. All right. So it means that if we could guess the right ansatz, which is this, which starts by 1 over epsilon, in principle, there would be a way we get it. Okay, so I have two objections against this. So first is we need to guess or to find out the right order of magnitude for the root, for the large root. Which is still alright, okay, because even just probe, trial and error could provide it, so that's maybe not a big deal. What worries me a little bit more is that the leading is in 1 over epsilon. And if you do things right in perturbation methods, the leading should not be in 1 over epsilon, because it means that at leading order, you're balancing things that are really large. So it means you look at a governing equation, translating, for instance, continuity or compatibility or equilibrium equation, and you just observe that at the leading term, at the leading order, when you look at the problem, you find a balance between things that are really large. And so it means that this is probably not the best way you should have used to set up the problem. All right, and so this means that in order to solve this, I'm going to address the other issue in a few minutes, but in order to address this issue of leading order of magnitude in the leading, we use something that is called rescaling. Okay, so let's assume that we know, and we'll determine this later, that the root x that we're looking for has order of magnitude 1 over epsilon. Okay, so we can redefine, or we can, define. So we can define another quantity, which is x tilde, which is going to be of order 1, because in any problem, if it is well posed, everything should be of order 1, including sometimes small quantities, but they should be explicitly stated by means of the small number epsilon, right? So if I define this, which is of order 1, by just saying that x is in fact equal to x tilde divided by epsilon. And indeed, if we do this, because x tilde is of order 1, x is then of order 1 over epsilon, and this works. Okay, so if we redefine x and get rid of x, we use a rescaled version of the problem. Okay, let's see what it gives. So the original equation was epsilon times x squared. So it means epsilon times x tilde square over epsilon square plus x minus 1 is equal to 0. And you see this equation, if I just simplify it, simplify the first term at least, let's say, is just rewritten in this way. And we have the same observation as before. Leading is large. So the governing equation here is large. Although this is something you did not really observe when you look at that equation here, that's not something that comes obvious, that when you're in the neighborhood of the large root, it's not obvious that this is super large. Although you understand x goes to infinity, so this is large. X goes to infinity much faster than epsilon here is small. So this second term here also goes large. All right, but this is much clearer. Now we have provided the rescaling. And so what do we do in order to have something that is of order 1 at leading? Of course, right away, we get rid of epsilon in the denominator and we multiply everything by epsilon. And so the new problem that we solve is x tilde square plus x tilde minus epsilon is equal to 1. And this is the new problem we want to solve. We're going to solve this problem for x tilde, and when x tilde is obtained, then we can compute x just by returning to the definition of x tilde. Okay, this is a rescaled version of the problem. Okay, and this is neat because at leading order, we have something that is of order 1. Same, of course, over here. At leading order, we'll obtain something that is of order 1. And so how do we solve this? This is a regular problem now, right? There's no reason for this equation to be singular. So we use a regular ansatz after rescaling. Regular ansatz after rescaling. And then we get x tilde is x0 plus epsilon x1 plus epsilon square x2 and so on. And then, of course, you understand we'll recover something that is exactly similar to what just earlier. So this is x0 square. I'll just put a few terms together and then we'll see how far we go with the solution. X squared, so this is the first one squared plus a double product plus terms of epsilon square will be twice x0, x2, and then we have x1 tilde square epsilon square then plus x0 tilde x1 tilde epsilon square x2 tilde minus epsilon. All of this is equal to epsilon to the third. And so at the leading now, okay, we feel, at least I do feel much more comfortable saying that the leading order now is of order 1. We have x0 square plus x0 is equal to 0, which gives us two options. This, which is rejected because x0 tilde can't be equal to 0, we end up with x0 tilde is equal to -1. Then at the next order, we end up with 2x0 x1 coming from here plus x1 tilde, tilde coming from there is equal to 0, which means that x1 is equal to -1, and so on, because we see we recover exactly the same things and same equations as we already had before. All right, and so at the end of the day, we find x tilde is equal to -1 minus epsilon plus order epsilon square, and then come back to the original quantities. X is x tilde over epsilon, so -1 over epsilon minus 1 plus things that are over epsilon. And we get it. Okay, this is a neat way to do. This is the neat and proper way to do. We use regular ansatz after rescaling. All right. Okay, so I suggest to have a short break over here. We will discuss later in the next video how we could have determined what is really important. This is the order of magnitude of the roots. All right, there will be different techniques for that, and they are going to be discussed in the next video. Okay, for now, keep in mind that a problem is either singular, either regular. Whenever a problem is singular, it doesn't mean it is singular everywhere. And so some part of the problem can be tackled with regular tools, like the regular ansatz. Use rescaling for the rest. And after rescaling, make sure the problem is now regular. All right, what still needs to be discussed, and that's what we're going to cover in the upcoming video, is how to rescale and how to change the original problem to something that can be used and tackled with the regular ansatz and things we know. All right, so I hope you enjoyed, and keep going.